Simple harmonic motion, mass and spring. Our objective is to determine the Hooke's law spring constant K of a vertically mounted spring. A static procedure will involve adding mass and measuring the stretch of the spring. A dynamic procedure will involve adding mass, setting the mass oscillating, and measuring the period. So for the static procedure, we'll add mass to the pan at the end of the spring and observe the stretch. Here, for example, is one block added to the pan and the spring stretched a little bit. It actually isn't necessary to know where the true equilibrium position is of the spring. We could even start here and say that the pan and the one block get it to this point and we don't have to worry about it. In other words, we'll only have to keep track of additional mass beyond this and the stretch from this equilibrium position. So if I go from 2 to 6 blocks, so that was a total of 5 blocks added from what's shown as the equilibrium line, then I can get the stretch for the 5 added blocks. And looking at the scale, that's 60 centimeters. So 60 centimeters is the stretch for 5 blocks added, and each block is 50 grams. So the essential idea is the weight mg equals the spring force K stretch kx. So K is the weight over the stretch, right? So if we take 250 grams, which is the 5 blocks, times G, 981, divide by 60 centimeters, we get K static is 4.09 times 10 to the third dynes per centimeter. Okay, so we're working in CGS family, centimeters, grams, seconds, force, and dynes. So for the dynamic procedure, we'll add blocks to the pan, we'll set the system oscillating, and to measure the period, it's actually better to measure 10 periods and then divide the resulting time by 10. So with your phone, with a stopwatch, you'll want to set we'll set the spring oscillating, and you'll want to start the stopwatch at a consistent point. Now I'm going to demonstrate using the lowest point in the oscillation. So here's how it would go. Start 1, 2, 3, right? And I stopped the animation here, but 3, 4, 5, you would go up to 10, and on 10 you would stop the stopwatch, right? So at the bottom of the oscillation, you're starting the stopwatch, and then you count 10 cycles, right, and stop the stopwatch, and then just divide that time by 10, and that is the period. So you'll record the period in a table, and the remaining slides show successively 1 block, 2, 3, all the way up to 6, right? And for each case, the system will be oscillating, and your job will be to measure the period. So with angular frequency being square root k over m, the frequency cycles per second being omega over 2 pi, and then the period in seconds, 1 over the frequency, we have that the period then is 2 pi times square root mass over spring constant k. Now it turns out if we square that, we get the period squared equals 4 pi squared m over k. And the reason for that is if we measure our data and plot t squared, tau squared, versus m, we get a straight line where the slope is 4 pi squared over k. So in other words, the spring constant k that we're looking for from this dynamic method will be 4 pi squared over the slope. And here is 1 block. 2 blocks. 3. 4. 5. 6 blocks. 'And there you have it. So we did the static procedure together and found the spring constant. Now, for the dynamic procedure, you'll need to get K dynamic, right? The spring constant from the dynamic procedure. So again, you have the period data for for the mass from 50 to 300, the period, and you squared that. So a graph of period squared versus added mass, we expect to be a straight line. Add a trend line that's linear, show the equation of that trend line, and get the slope. And then the spring constant that we're looking for is 4 pi squared divided by that slope.